In the last video, we saw that a dynamic array is fast at almost everything, except inserting or removing near the front, where every single element has to shift over. If your program does that constantly, all that shifting adds up. So, what if there were a structure where adding or removing an element never forced anything else to move? That is exactly what a linked list gives you. And today, we will see precisely how. A linked list is a chain of small, separate objects called nodes. Each node holds two things: a piece of data and a link, a pointer, to the next node in the chain. Instead of living in one solid block like an array, the nodes can sit anywhere in memory, held together only by these links. Follow the links from the first node to the last, and you have walked the entire list. Let us look at a single node closely. It has two parts. The first part stores the value, here the number 10. The second part stores a reference to the next node, not the next value itself, but the address of where to find it. That second part is the pointer. This tiny pairing, a value plus a pointer to the next node, is the entire idea a linked list is built from. The list itself only needs to remember one thing: a pointer to the very first node, called the head. From the head, you can reach every other node by following the links. The last node is the tail, and its next pointer points to nothing. We call that null, and it is how we know the list has ended. Some lists also keep a direct pointer to the tail, which, as we will see, makes adding to the end much faster. This is the deepest difference from an array. An array is one continuous block of memory, every element side by side. A linked list is the opposite. Its nodes can be scattered all over memory in any order, and the pointers are what stitch them into a sequence. This freedom is the linked list's superpower and also the source of its main weakness. Because the nodes are scattered, there is only one way to move through a linked list. Start at the head and follow the next pointers, one node at a time. You cannot peek ahead or jump around, you walk the chain link by link. This single fact explains the cost of almost every linked list operation. Suppose you want the element at index 3. An array would jump straight there in one step. A linked list cannot. It has no formula for where index 3 is, because the nodes are not in a row. So it starts at the head and walks forward 3 times, counting as it goes. Reaching a position takes time proportional to how far in it is. Access by index is O of n. This is the price of all that flexibility. Now the payoff. To add a value to the front of the list, you create a new node, point its next at the current head, and then move the head to the new node. That is it. 2 pointer changes. Nothing else in the list moves, no matter how long it is. Inserting at the head is O of 1, constant time, exactly the operation that was slow in an array. Adding to the end depends on what the list remembers. If it keeps a tail pointer, it jumps straight to the last node, links it to the new node, and updates the tail, constant time, O of 1. But if it only knows the head, it must first walk all the way to the end to find the last node, which is O of n. This is why many real linked lists keep a tail pointer. Inserting in the middle is where linked lists shine. Once you are standing at the node you want to insert after, you only rewire 2 pointers. The new node points to what came next, and the previous node points to the new node. No elements shift over. The work is constant, O of 1. The catch is in those words. Once you are standing there, getting to that spot still means walking from the head, which is O of n. Deleting works the same way and is just as cheap to perform. To remove a node, you make the previous node's next pointer skip over it and point to the node after. The removed node is now unreachable, so it gets cleaned up. Again, the rewiring itself is O of 1. The only cost is walking to find the node first. What if you are looking for a value, not a position? Just like an array, a linked list has no shortcut. It starts at the head and compares each node's data one by one until it finds a match or hits the end. Searching is O of n, and if fast membership checks are what you really need, a hash set from our earlier video is still the right tool. So far, we have drawn a singly linked list. Each node knows only the next one. A doubly linked list adds a second pointer in every node, one to the next node and one to the previous node. That lets you walk the list backwards as well as forwards, and it makes deleting a node easier because the node already knows who comes before it. The cost is a little more memory and a little more pointer bookkeeping on every change. There is also a circular variation, where the last node points back to the first instead of to null, forming a loop. It is handy for things that cycle naturally, like taking turns around a table or a round-robin scheduler, letting you keep moving from the end straight back to the beginning. Let us gather the costs. Reaching a position or searching for a value is O of n, because you must walk the chain. But inserting or removing at the head is O of 1. At the tail, it is O of 1 when you keep a tail pointer. And anywhere in the middle, the rewiring itself is O of 1 once you are there. The pattern is clear. Linked lists are slow to find things, but fast to change structure. Put side by side with a dynamic array, a linked list is almost a mirror image. The array stores everything in one block, so jumping to an index is instant, but inserting in the middle is slow. The linked list scatters its nodes, so inserting or removing is cheap, but reaching an index is slow. There is no single best one. The right choice depends entirely on which operations your program does most. So, when should you choose a linked list? Reach for one when you constantly add and remove at the ends. It is the natural backbone for queues and double-ended queues, or when you rarely need to jump to a position by index. Avoid it when you need fast random access by index, when memory and cache performance are critical, since scattered nodes are cache unfriendly, or when you only care about membership, where a hash set wins. For most everyday, just hold a list of things tasks. A dynamic array is still the default. A nice way to picture a linked list is a train. The engine is the head, and each car is coupled to the next. The coupler is the pointer. To add a car in the middle, you do not slide every other car along the track. You just unhook one coupling and hook in the new car. To remove one, you recouple around it. The cars never have to shuffle their positions exactly how a linked list inserts and deletes. In code, Java gives you a ready-made linked list that supports adding and removing from both ends in constant time. And you can also build your own from a simple node class holding a value and a next reference. Python does not have a built-in linked list, but you can write the same node class, and in practice, when people want fast operations at both ends, they reach for collections.deque, which is backed by a doubly linked structure. 2 reminders. There is no random access here, so looping is how you reach a position, and always update your pointers in the right order so you never lose the rest of the list. So, to summarize, a linked list is a chain of nodes, each holding a value and a pointer to the next. There is no contiguous block and no index math, so reaching a position or searching is O of n. But inserting and removing are O of 1 once you are at the spot. Because you only rewire a couple of pointers, nothing shifts. Doubly linked lists add a backward pointer for two-way travel. Choose a linked list for heavy insertion and removal, especially at the ends, and a dynamic array when you need fast access by index. If this made it click, please subscribe for more visual explanations. Next up, stacks and queues explained visually.